So yeah, verified boot, surviving in the Internet of Insecure Things, the catchy title that hopefully grabbed you all in. So who am I? I've been a Chrome OS firmware engineer since 2009, so actually more than 7 years now. It's the longest I've ever done any one thing, even including my PhD thesis. I'm co-architect of the Chrome OS verified boot reference code. Today I'm actually coming in and talking more as how do we take this and extend this past just the good things we're doing in Chrome OS and getting it into a wider audience. So what do we really want? We want verified boot and firmware. We want something that's secure. We want it to be robust. We'd like it to be open. And we'd like it about 7 years ago. Sooner would be better, but I'll take 7 years ago. So back in 2009, when we started on Chrome OS, we were focused on boot security for a new open source laptop. It's a pretty familiar scenario for those of us that have been working on BIOS and firmware for a lot longer time, even though we were doing some kind of cool new things. But now in 2016, there's a lot more devices out there. It's not just laptops. It's phones, it's tablets, it's refrigerators, it's routers, it's webcams, it's thermostats, TVs, light bulbs, everything. All of them have boot firmware. Many of them have upgradable software. Every week I get to read about a new exploit in one of these things, and it's kind of terrifying. You can't be sure what's actually in your house or what's in your place of work and what's controlling things. So what am I going to talk about? I'll talk a bit about what is verified boot. Why do we want to do the things that we do? I'll talk a bit about the sort of the simplified boot flow of what verified boot does. There's actually a lot more complexity in all the little details of why particular things are the way they are, but I'll sort of cover it at a high level. I'll talk a bit about how verified boot is integrated into coreboot today. Hopefully I'll have some time to talk about what's coming next, some of the things that we're doing, some of the things that we're starting to think about for verified boot in the future, and a little bit of how you can help too. So what is verified boot? It means different things to different people. If you're a normal user with a device, verified boot means to you that you can trust that your device is running official stuff, firmware, OS, whatever, and you can trust that. If you're an open source developer, what verified boot means to you is that it's running your stuff, and you can trust that it's actually running your stuff. If you're an open source user, and there are a lot more open source users than developers, people running Crouton, people running, just taking somebody else's distro and putting it on their device, they want to be able to verify that it's actually running that distro and not some other thing. Content providers, much as I hate DRM, and I'll probably say that repeatedly during this talk, they do own their own stuff. They would like to be able to trust that when that stuff is being played through a device, that it's not leaking their content out to the internets. Enterprise and education are sort of an interesting use case. Enterprise, which is what we started off thinking about in Chrome OS, it was most of the data is in the cloud. Enterprise cares mostly about how that data is being accessed. But they don't care quite as much about the devices themselves. If you go do something horrible to your device, as long as in the process of doing that, it locks you out of their data in the cloud, they care less. And that was one of the great things about Chromebooks is that we weren't putting data locally other than cache. Education is sort of a new focus for us because Chromebooks and education are huge. I won't quote numbers, but there's a lot of them out there. If you have a kid in the school, they probably have Chromebooks in their school. Education cares about preventing unauthorized use of the device itself. And so that makes this a separate interesting problem because for verified boot for them, it means it's running official stuff I trust, but I don't actually trust my users anymore. Note that this is not about carriers selling lockdown systems with bloatware. This is really about the owner of the device being able to control it. So what do we want to protect? We want to protect user and third-party data, whether it's on the device or in the cloud. We want to protect the owner's control of the software running on the device. We want to stop them from, stop the device from being able to be part of a botnet. We want to protect from ransomware, denial of service attacks. And like I said, there's this interesting case where schools in some cases even have legal requirements to limit what the students do with the laptops. If you remember a few years ago when the LA school districts gave out iPads and they all, within the course of a couple of months, disappeared from the school's reporting infrastructure, and the students were running all manner of things on them, from Minecraft to the sorts of things you would expect teenagers to do with access to the internet. So who are we protecting against? The most important use case that we care about is protecting against remote attackers. They can mass compromise devices across the internet. They can, install, make huge botnets. Ransomware is real popular out there right now. Temporary attacks at the operating system level are inevitable. Much as we would like to prevent them, and where we succeeded at the first couple of years of contests like Pwn to Own, when you have the attack surface of an entire browser and plugins and applications, it's inevitable you're going to have temporary compromises. But what we really want to stop with verified boot are persistent compromises. If I take my device and I hard reboot it, that should take me through a verified boot flow that gets me back to a secure system that I can trust, or gives up and says, hey, I don't actually have anything that I trust that I can run. You probably ought to fix me now. So that's our most important use case of those remote attackers. We care some about casual local attackers in classrooms, libraries, coffee shops, offices. When you all walked out of the room to go get snacks after the first talk, we don't want someone to be able to walk by your devices that are running Chrome OS, that are running our open source firmware, and be able to sort of stick a USB key in each one and own each device as they walk back and forth the tables, and in 20 minutes they've owned all of your computers. We'd like to protect that sort of casual attack. We have a new use case with the education market of local attackers with long-term access but not specialized tools. Students, it turns out, are actually willing to use a screwdriver. A soldering iron is still a little bit past where most of them are. They can follow YouTube videos. They're actually brilliant at following YouTube videos. My son was able to get CyanogenMod onto my old Android phone with no problem, even though it took him a few hours. And certainly anything that they can follow at that level, they will do to break out of their enterprise enrollment so they can use the devices how they really want. A case that we're not really focused on right now are the local attackers with specialized tools, professional attackers, people willing to do board level mods. If you're willing to replace components on the motherboard, if you're willing to cut traces, you probably can do whatever you want anyway. There's really no feasible way we can stop you short of filling the entire case with epoxy. And even then, you can very carefully dig through the epoxy and get to the devices. We're not worried about compromised attacks using specialized tools like RF antennas, clock glitching, freezing parts of the RAM and doing cold boot attacks, decapping parts. Those are really impossible to stop at the level of verified boot. Now, you can certainly harden laptops. You can certainly put hardened chips in if that's sort of out of the scope of verified boot as I'm talking about it today, which is at a general software level. Verified boot really is only as secure as where you start. Some devices start with mask ROM and e-fused keys. They're very secure. They're also usually very closed source. It's also unclear in the cases where they're doing that verification on chip in the mask ROM. Are there any backdoors in that? Are there any extra keys they're not telling us about? So they will sign our, you can provide your own keys and fuse them in, but is there a second set of keys fused in there for the manufacturer? Is there a second set of keys fused in there for some three-letter acronym government organization? We worry about things like that. And who holds those signing keys? Who can sign firmware for that? So we like SpyFlash. SpyFlash can be made physically read-only if you pull the right protect pin and configure it properly. We can put our first stage firmware in there. We can put our verification keys in there. You can change it if you want. If you crack open the device and you use a screwdriver to pull out the right protect screw, and you have control of the device so you can actually run flash ROM, you can change all that. You can verify what code is actually in there and being run. We worry about other things too. We worry about eMMC, SATA, NVMe, all those other disk storage. Those disk controllers have their own upgradable firmware. And so when you look at a device and you say, well, gosh, that SpyFlash is inconvenient. I'd really like to drop that 25-cent part. Can't you just boot straight from eMMC? The answer is, yeah, but I don't really believe it's read-only story. I don't believe that necessarily, as it remaps all of its sectors, that its controller firmware is actually robust against attack. And I can't see what it's doing because just like the mask ROM, it's closed source firmware. I don't know what's in there. So that's why in all the Chromebooks, we actually stuffed a spy flash in. Verified boot is only as secure as the worst bug that you can patch. So we want our read-only boot stage to do as little as possible. Very small attack surface, no network access. Ideally, even RAM init is not part of the read-only boot stage. We'd really like that to be in read-write. That's something we were working on. I don't know if any of you are familiar with the rowhammer bug that was disclosed last year, where it turns out that if you configure your RAM improperly, there are various attacks that you can do to compromise the system. If you want to change that, you've got to change how RAM is initialized. Gosh, wouldn't it be nice if that were in patchable read-write code? For those later stages of code, for those read-write firmware stages, we need rollback protection. And what I mean by that is you can't, once we've put a new version of the firmware on the device, you can't roll back to an old version of that firmware that had a worse compromise. To do that, we need some lockable non-volatile storage because we need to store in that storage the minimum version we're going to accept. And we need to lock that so you can't compromise that at a later point in time. If you get root on a system and you can go in and back up the firmware and back up the minimum allowed version, now a small compromise in the current code can allow you to back up to an old version of the firmware that had a bad persistent compromise. Keys leak also, so any keys that we're going to be taking out and signing things with frequently, we'd better make those rollable too. So we have a whole successive stage of keys from things that are in the read-only firmware out to rollable keys in multiple stages. I'll talk about that later in the idealized boot flow. We'd also like updates to be painless and acknowledge that sometimes we may screw up and push out a firmware update that can fail. So we have multiple copies of the read-write firmware. We have one copy that we'd like to be good at all times. We'll have another copy, a B copy, that we can update. We can set a flag in RAM and CMOS to say, try that new copy next time. That also allows us to update that copy in the background. One of the really cool things about Chrome OS is most of the updates happen, you're completely unaware they're doing them. You just get that little arrow in the bottom of your screen that says, oh, you should really turn me off and on again, and you'll get the new goodness. But since we have the multiple copies, if that new firmware doesn't take, we can back up to the current one. Next row, there we go. So we also want a robust read-only recovery path, because sometimes we mess up. Sometimes there is a persistent compromise. We'd like to be able to unpersist that. So a read-only recovery path is in the read-only firmware. It has to be in the read-only firmware because the read-write firmware might be corrupted. If you trash everything that's on the disk, if you trash everything that you can hose with flash ROM, with root access on your device, the recovery path should still be there and be able to get you back to a sane place that you can then reinstall the OS from. The recovery path itself, we want to be very simple because it itself is an attack vector for local attackers. If I can walk over to your machine, reboot it into recovery mode, stick in a compromised recovery stick, that's not so good either. So we really try and keep that recovery path small and simple. It's part of why we don't do network recovery, because network recovery is hard. Network stacks are a big attack surface. Again, periodically you read about, oh, look, here's this new exploit in this networking library. If that were in read-only, that recovery path might be exploitable that way. The other problem is we can't update network certificates if they're stored in the read-only. So if you have a device that was made 4 years ago and you put it in recovery mode and there were a network recovery mode that's using some 4-year-old cert, somebody else could be impersonating the official source of recovery material, and that lets them inject old code onto your system, perhaps get control of your system that way. Another important way, so for recovery mode, we'd like it to be triggered automatically on boot failure. If your system is booting up and it's verifying each stage and it says, wait, I've got nothing good for the next stage, it should keel over, it should reboot to a read-only firmware screen that says, hey, I can't verify your firmware. Could you please, I can't verify your OS. Could you please fix me? But we also need to have manual triggering of recovery mode. And this is important for that persistent case. If there were something in the operating system that when it starts up and it starts loading your Chrome extensions, or it starts loading something else that's persistent for you at boot time, And in the process of doing that, your system gets owned. You need a way to interrupt that boot flow to say, hey, no, wait, this time I only want to boot the read-only stuff. I want to get back to code that will allow me to install that fresh operating system that I trust again. So that manual triggering is a very important part of recovery. Okay, so what about open source developers and users? Very important, if we're an open source operating system with an open source browser running open source firmware, it would be kind of frustrating if the devices that had this on them were locked down with those effused keys and using the mask ROM such that you couldn't actually install your own. We really want this to be developable both at the OS and firmware levels. We want developers to have access to all the functionality in the device. We don't want to lock you out of things in the process of making this firmware verified. Almost. Pre-installed content keys, it's kind of fair to lock those out because the content owner can't necessarily trust what you're doing. Now, that doesn't mean you can't install your own keys if you have some other source to get them from, but just when they're putting those keys into the device in the factory, and I'll talk more about this a little bit later in the what's coming, they're putting them in the factory assuming that it's running official stuff. So if you're running official stuff, unofficial stuff, maybe you can't get to those, but you still should have full access to all of the media codecs, all of the ability, if you have your own ways of accessing that protected content, that you still should be able to do that on your device. Another important thing, and we had a big fight about this way back 7 years ago at the start of Chrome OS, is what developer mode means. Developer mode should not mean insecure mode. If you're putting your own firmware on this, if you're putting your own OS on this device, you shouldn't have to give up your ability to secure your device just so you can run unofficial stuff. It's not like there's a secure and insecure switch. You should be able to protect your own stuff as well. So I'll talk a little bit more about developer modes. There's sort of two levels of developerness in verified boot. One is for the people that want to run their own operating system, but they don't really want to change the firmware. These are the people that want to run Crouton, you want to run stock Ubuntu on your system, whatever. You need physical access to enable any of these developer modes. That's important because that stops the remote attacks, where if I can switch your device into developer mode so it's willing to run code that's unofficial code, if I could do that en masse to every Chrome OS user, a lot of them probably aren't going to be sophisticated enough to figure out what's going on. So they have to be local there. We also want to have a warning screen when a device is in developer mode, so you have some way of knowing that your device is running unprotected content, unprotected system software. Then there's the firmware developers, which includes all of us. If you're going to go change the firmware, we can't really put a warning screen up on the system, because what puts the warning screen up on the screen is the firmware which we are intent on changing. So for this, we want it to be a little bit more difficult. We want you to actually have to take the device and have it for long periods of time and maybe crack the case open. Because we want to stop the casual attacks. You know, if I can casually walk down your system and I reboot it and I install something else and I put it in developer mode to do it, and you come back to your Chromebook and you say, you know, I don't remember logging out. I'm just going to reboot this thing. And when you reboot it, it pops up a warning screen that says, hey, verification is turned off. It may occur to you that something is wrong. Hopefully it occurs to you that something is wrong. But if I go and I can change your firmware, you're going to have no clue that anything is wrong. So we want putting developer firmware on a device to take longer, be more intrusive, so that when you're out there looking, it's like, that's funny. How come that guy's unscrewing the backs of everyone's laptops? There's a higher chance of catching them doing that. Hopefully you would say something. It's also, this is where we get back to the enterprise case, the education case. This becomes more entertaining for schools because it turns out that students have long-term access to these devices, but we still want to be able to stop them from getting into developer mode. So I'm working on some things with that. One important thing with that is it needs to be reversible. If we can lock out developer mode, we need to be able to re-enable developer mode so that devices, when they're resold, whether they're resold to students or anybody else, if a corporation goes under, if they want to end of life their devices, that those devices can be reused for development after that point. So anything that they can do to disable developer modes, we need to have a path for re-enabling them again later when the owner changes and that new owner says, no, I really want to be able to develop on this. Performance matters here too. some ARM, verified boot really shouldn't hurt your boot time. If verified boot was perfect and secure and it took 5 minutes to boot, we would call it Android. Except for the perfect and secure part. But hopefully we'll fix that. We want to verify only what we need at each stage. So we want to have that small footprint at the beginning, and this plays in a little bit to like some of the code, some of what we talked about in the last talk with Apollo Lake and having minimal code that you want at the early stages, so you don't load a whole bunch of stuff that painfully as you're transitioning out of cache as RAM. Same sort of thing here. We don't want to, we may be booting, some of the ARM processors boot the little security processor first. And that security processor is like a 100 megahertz Cortex-M or Cortex-R processor. Not super beefy, not a huge amount of RAM available on it. Doing really strong crypto on that is kind of slow. And we'd really prefer not to slow down the boot time because we want you to reboot your system frequently. We don't want to force you to, but we want you to feel okay doing it. So when you come back to your device, if you're not sure what the state of your device is, you think, I'll just reboot it. And I know that when I reboot it, unless somebody has actually cracked open my case, I know that it's going to go through this verified boot flow and I can believe what it's running after that. So there's some trade-offs with performance. We can use really strong keys. We could use 81, 92-bit RSA keys. Those turn out to be actually a little bit slow on some of the ARM processors. We don't want to run really short keys. Those might be easily crackable. Quantum crypto isn't here yet, but we are thinking about those sorts of things. You can have hardware crypto on some of these systems that can speed up that little slow processor. But again, now we're trusting code that we can't quite see. If it's a software crypto algorithm, I can be pretty sure what it's doing. If it's a hardware crypto engine, is there some little back door in there where if you feed in something, it says, yeah, that's fine, even though it wasn't. So when we use hardware crypto, we make sure that we can actually fall back to software crypto as we transition through the keys so that we're not susceptible to any bugs in that. We want to be able to patch the hardware crypto out of our boot flow. So next I'll talk a little bit about how verified boot flow works, at least in a little bit simple case. Like I said, there's a lot more details if you actually dig down into the code, into some of the design docs. But this is sort of a high-level approach of it. So we start out with our read-only firmware, which, like I said, usually is sitting in SPI flash because we actually believe that read-only story. The very first thing we do is we do that manual recovery check. And we do that very first because that way nothing can block it. Nothing can get in the way of that. So if you have a Chromebook and you do power refresh escape, that triggers a hard reset of the system. As it's coming up from that hard reset, one of the first things it does is looks to see, well, what keys are held down on the matrix keyboard. If it's those keys, I'm going to go straight to recovery mode. I'm not going to look at what's in read-write flash. I'm not going to look at what's on the disk. I'm going straight to recovery mode so that hopefully I can patch whatever's wrong with the rewritable stuff on my system. We make that automatic recovery check from CMOS, from that other, non-volatile but not lockable storage. So in case in the previous boot something didn't verify, we got to kernel verification and the OS didn't verify, the rootfs was corrupt. Any of those things can request that the system reboot, come back into recovery mode. Assuming that we're not going to recovery mode, which I'll talk more about in 2 or 3 slides, then we want to check our rewritable firmware. Like I said, we've got multiple firmware slots. We check both. We check them in order. We verify firmware. Like I said, we have cascading keys. So that root key from read-only we use to verify a firmware data key. That firmware data key is to verify the firmware payload. And both the key and the payload have version numbers that we have rollback protected. So after we verify the firmware, if we like the firmware, it's good. Obviously, if we didn't like A, we'd try B, or if we were trying B and we didn't like B, we'd fall back to A. But after we figure out which firmware we like and it's good, we look to say, well, do we need to update the version in that non-volatile storage? Do we need to move the bar up and say, those older versions we're not going to allow to run anymore? If we do, if that's needed, we update that non-volatile storage that has the firmware versions in it. And whether we update it or not, we lock that first firmware version storage space before we jump to the read-write firmware. And that's really important because that means that if the read-write firmware has a bug, it can't roll itself back. The only way to roll back the firmware would be to actually have some bug in the read-only firmware that would allow you to roll back that storage because it's locked by the time the read-write firmware runs. So the rewritable firmware, this is where most of the interesting stuff happens. We're initializing more of our components in our devices. We're initializing DRAM. We're initializing storage. We might or might not actually be initializing display, keyboard, and USB. When we started out, the video BIOS on the systems was kind of slow. And we thought, well, why are we initializing the video BIOS in the firmware when we don't actually have a BIOS screen to display in the normal boot mode? We'll just leave that. We'll let the kernel initialize it. Some of the ARM chips initializing the display is very fast, so nobody cares. We might or might not be initializing keyboard and USB in the normal boot flow because, again, there's no, if you're booting normally, there's no warning screen. There's nothing, there's no keyboard, no keys you could press other than checking those initial recovery combination in the read-only firmware. So then we're going to check for developer OS mode. Remember, developer firmware mode is changing this read-write firmware. Developer OS mode is just changing the OS. So in that lockable storage, in that lockable firmware storage, we have a flag that says, am I willing to run an operating system that is not the official one? If that flag is set, then it bypasses the kernel data key check, which I'll talk about in the next slide, and lets you run whatever kernel data key you want, more or less. There's a warning screen there that will pop up. So we actually want to throw something up on the screen that says, hey, I'm about to leave verified land into, I don't know what you're going to run. Up to you, do you want to continue or not? We had a lot of entertaining discussion about the warning screen when we were developing Chromebooks as well. We have a 30-second timeout on the screen. The security folks said, no, it's got to stay up there until the user explicitly confirms it. We said, no, we want a 30-second timeout because we may be using this in an unattended system. If you take your device, flip it into developer mode and say, I want to use this as my media server and stuff it in my closet, and your power glitches, you don't really want to have to go home, go to your closet, open up the closet, and press a key on the keyboard to continue. 30 seconds ought to be enough if you're at the device. There's also a key combination you can bypass the warning screen with. So if you press Control-D at that dev warning screen, it bypasses it. Because if, as a developer, every time I booted my device, it made me sit there and wait 30 seconds before I could boot the thing, I would be really, really frustrated. That would encourage me to find ways to hack Chrome OS. And I'm really trying not to encourage people to find ways around it. If I can make it painless for you, you can just use it. You don't have to find extra vulnerabilities. Minimize the number of people that don't like me enough to attack my stuff. Normal users, from that warning screen, we also wanted to make it really easy for normal users to say, oh, wait, how did this happen? Because we worry about the case, or as a personal case, if my kids go up to my grandparents' house and my grandparents have, or my parents' house, and my parents have a Chromebook, and my kids say, well, I want to play Minecraft. So I'm going to flip this thing into developer mode. I'm going to run Crouton on it because they're well capable of doing that. And then they go back home, and now my parents reboot their Chromebook, and they see this warning screen that says, huh, you're not running Chrome OS anymore. I want it to be really easy for them to say, no, I really do just want to run the official Chrome OS, because whatever my kids have put on there, it may not get auto updates. Even if it was they started a month or two from now when there's some vulnerability we need to patch, I want it to be very easy for normal users to get back into that verified mode. So normal users from that screen can say, oops, take me back to the land of verification. If you've turned on legacy booting USB, booting USB or legacy BIOS as a developer, that warning screen is also where you can press a couple of other key combinations to get into trying to boot from USB or trying to boot from a legacy BIOS. So more of the read-write firmware. The next thing we do, we check the OS kernel. And this looks an awful lot like what we were doing when we were checking the firmware, and it is. It's just in a later boot stage. We have multiple kernel partitions sitting in a GPT-based disk. Those kernel partitions have some additional bits in the GPT to indicate which ones we should try first. Should we assume it's good, or should we only try this partition a couple of times and give up on it? But anyway, we have multiple kernels just like we have multiple firmware slots. And again, that lets us do updates in the background. We verify that kernel data key using a kernel subkey. Like I said, there's a whole connected linked list of keys. That kernel subkey lives in the read-write firmware. Unless we were in developer OS mode, in which case any kernel key will do. We'll trust anything. We're actually doing some kind of cool things now to actually make it possible for OS developers to specify their own key and load that into the system, where it will only trust that developer key at that point. Because, again, we don't want turning on developer modes to mean turning on insecure mode. We really want this to be just as secureable for developers. We verify that kernel payload using that kernel data key. So again, there's this link of keys so that we can roll the keys and we can roll the kernel version as well. Rollback protection here works the same as it does in the firmware, but we have a different lockable space because remember, the firmware space we already locked. We have a kernel version space that we can lock here that stores the minimum versions of OS that we like. We roll that forward if we found a new OS that we liked, that we verified that it previously booted and said it was successful. And then we lock that. Then we jump to the OS kernel. At that point in time, when you talk to Chrome OS developers, they will tell you all sorts of wonderful things that the OS will do. At that point, I see a splash screen on my computer that says, you know, sort of now booting Chrome OS, the little Chrome logo. At that point, I'm done. I'm perfectly happy. Life is good. Hopefully, that whole process took only a second or two. Really, I'd like less than a second. Okay, recovery mode. So what happens if all of that didn't verify? Remember, recovery mode we can trigger manually. It could be triggered automatically if that read-write process that verification process that we talked about failed. We display a recovery screen. On the current Chrome OS, we wait for users to insert recovery media. So we basically say, I'm broken. Here's a URL. Go to this URL. It will tell you how to download an operating system onto a USB stick. Stick that in me. I'll fix myself. We use a different key for verifying that recovery media than the keys we used for the normal boot flow. There's some interesting tidbits about that. We don't have rollback protection for recovery mode because it's unclear when it would be safe to actually roll that minimum version forward. We also were worried about the case of what if we actually had a bug in our roll forward process. And actually, it turns out way back in the beginning of Chrome OS about 6 years ago, we did have a bug where we wrote FFFFFFF into the minimum version that we would allow to boot. That's obviously bad. At that point, we could have released a firmware with version FFFFFF, but then at that point, if we find a bug in that, we've exhausted our version space. We can't fix that. So we don't have rollback protection in recovery mode because we want to be able to always boot recovery mode. Recovery mode always has to work. And there isn't a developer mode straight in recovery mode. You can't force a device into developer mode and then boot anything you want from that recovery mode because then again, it makes the device insecurable for developers. I could walk up to your device, you know, reboot into turn developer mode on quickly, reboot into recovery mode, stick my own thing in and boot it. Now I've owned you. Hopefully you'd at least notice, but I've still owned you. At the very least, I've been able to wipe out what's in your system. Maybe I could read what's on your system, and where hopefully it's encrypted, I can still snarf it down and do offline attacks against it. When we boot in recovery mode, we do leave those non-volatile spaces unlocked at the beginning of recovery mode, because like I said, we could break them, and in the past, we actually have. But the first thing the recovery image does when it runs that OS is it locks those spaces again. More or less, we leave the door open and then we slam it shut, but we retain the capability, if we ever wanted to release a recovery OS image, which did fix those spaces. And there we would do the minimum possible fix. You know, if there were some fix, you know, some bug that always wrote dead beef into the version, we could make a recovery image that looked specifically for, okay, for that model Chromebook, if we see dead beef in the version, then we know the right answer should be 6. So it's not wide open. So we can sort of open the minimal hole we need to fix whatever bug we actually run into. Then a local user, so how do you get into developer mode on these devices? We do it from the recovery firmware screen because at that point we actually trust what's running. It's read-only code. We know it's talking to local things. It's not talking to a network stack. So at that point on your Chromebook, if you manually trigger recovery, you can press Control-D on that recovery screen, and it'll say, do you want to enable developer mode? And you can say yes at that point. But you've had to physically be at the device, the TPM owner, so it clears out the encryption keys for your local storage. So yes, you've enabled developer mode, but now all of that stuff on your disk is inaccessible. So we're at least protecting your data. And then we store that flag, that developer flag, in that lockable NV storage, which was unlocked just long enough because we're still in the firmware when we're doing this enabling of developer OS mode. That space is still unlocked. We can set the flag in there. And now you're in developer mode. Okay, so I alluded to there being lots of keys. We like keys. We like chains of keys more specifically. So I'll talk a little bit about the keys. So we start out with a root key. That root key lives in the read-only firmware, or lives next to the read-only firmware. It's not versioned because it's read-only. When would we ever be able to rev it? That's going to verify the firmware data key. And the important thing here is that root key, we basically never have to pull out the private half of that key. The only time we have to pull out the private half of that key is to sign a new firmware data key. That's all the root key does. So we can keep that key in a locked room guarded by laser sharks, with card key access on the door to where you need N of M people to get through the door. We can really keep that locked down, in an undisclosed yet secure location. That's also the one where we use our strongest key strength on it. At least 4096-bit RSA in all of our current implementations. Some of the Chromebooks, particularly the ones using Intel chips, use 8192-bit RSA. Is there really a practical difference between 4096 and 8192? Yes, if you're marketing. So that's kind of why we did. Now the firmware data key, that's the one that actually gets used to sign the read-write firmware. So that one, every time we do a new firmware update, we've actually got to pull that key out, sign stuff with it. But if that signing server, and that lives on the private half lives on a signing server somewhere, if that key got compromised, all we'd have to do is go into the secret room with the laser sharks with our N of M people, sign a new firmware data key with a higher version number, use that to sign our firmware next, and as soon as we push that out to users, the rollback protection will lock out that old vulnerable compromised firmware data key. So we can protect, we can close those security holes as long as it's just the firmware data key that's compromised. Obviously, if we lose the root key, it's kind of game over. It's a permanent compromise. There's no way to resecure those systems. But that's why we have this. That's why we have this two-step key process, so that we can protect against those. The kernel subkey lives inside the read-write firmware, and again, this is only used to sign the kernel data key. This is kind of an extra step because really the kernel subkey is also rotatable when you do a firmware update. But doing this allowed us to reuse the same code that for kernel verification as we do for firmware verification. Code reuse is good. Kernel data key, again, can be revved. It lives on the signing server. And you notice the key strength sort of drops down as you go through that over time. But that key, the strength of the key is actually stored inside the key, the signed part of the key itself. So if we wanted that root key, that 4096-bit key, if we said, firmware key is a 4096, kernel subkey is a 4096, if RSA 2048 isn't good enough anymore, we could say, okay, we're going to roll that key forward, we're going to make a new kernel data key, and now it's going to be a 4096-bit key. We can do that in any Chromebook we've ever shipped. Because the encryption, the key length is one of those things that we can update in that key header. So then the other key that we have is that recovery key. Like I said, that one's also precious because it lives in the read-only firmware. If it gets compromised, now you can run anything you want in recovery mode. That's obviously not so good, especially considering we leave everything unlocked when we first hit recovery mode. So we guard that with the locked room and the laser sharks again. The important thing here is it's only signing the recovery installer operating system. It's not signing the recovery payload. So that installer, more or less, all it's doing is saying, okay, you're in recovery mode. I'm going to take this payload. I'm going to check it using the root key, using the normal key ladder. If it verifies, I'll be willing to throw it on your disk for you. That installer changes very infrequently, very, very infrequently. So again, we're not having to go to that locked room to sign that recovery payload very frequently, which is good because the sharks are hungry. And it's hard to, actually, the real problem, it's hard to get N of M people in a room. Okay, so verified boot in coreboot today. There we go, Vboot reference. Okay, so sort of three pieces here. Vboot reference is the actual source code that I maintain and love. It's a reference library that's called by coreboot and Depthcharge. It's got a couple of different directories of stuff in here. I'm going to sort of leave this here, assuming the slides are available afterwards, and not talk to this in too much detail. Sort of the important piece here is we have a couple of different sub-libraries. We used to have a library that was sort of the Vboot 1.0 code. That was a little bit clunky of an interface, partially because we designed it to be called by UEFI firmware, which we didn't really trust. We didn't trust a lot of its API. We didn't want it to be sort of a fine-grained interface. We really wanted to have the minimal API necessary from the large, confusing, ugly thing to our beautiful code. Now that we're tying in more tightly with coreboot and Depthcharge, we are more willing to have a finer-grained interface talking from elegant, beautiful code to elegant, beautiful code. So that's what Vboot 2 is. Firmware verification, the firmware verification step for that is up. That was checked in a year or two ago. I'm working now on porting the kernel verification code to that finer grained API as well. We also have some libraries for parsing the GPT and for software crypto. So inside coreboot itself, like I said, we're using the Vboot Reference 2.0 APIs. Those are the files that are the interesting ones. Like I said, go take a look. So Depthcharge is how we're doing the kernel verification. Like I said, very similar light code. This is still using the old Vboot APIs. I kind of want to fix this because it's kind of ugly. So we've got some thin wrappers there around VB select and load kernel, where basically the entire world of kernel verification lives inside that function. It calls back to screens.c to say, hey, I would like you to display the dev screen or the insert screen, but it's not really set up for a good, more flexible UI. There's some other callbacks that we call back to read or write a sector-based disk, to get keystrokes, to read that lockable, the non-lockable storage for settings, CMOS. There's a TPM layer where we call up for TPM calls. But again, right now that's a little bit clunky because we do all of the mid-level TPM stuff inside this Vboot 1 library. We don't actually call out to a TPM library and say, hey, could you create a non-volatile storage space for us? That's some of the stuff that we'd like to fix. So what's coming next? Oh, I'm actually doing pretty well on time. So form factors. Form factors are changing. When we first started on Chrome OS, our focus were Chromebooks. And a Chromebook is a laptop. It's got an internal matrix keyboard. It's got a screen. It's got batteries. It's a fully featured, simple laptop, just what you'd like. Then we got Chrome boxes, which are sort of like Chromebooks if you take away the battery and the screen and put a USB keyboard on them. Now we've got tablets and routers. There's a Pixel C keyboard that at its core, deep down inside it, runs our verified boot stack, even though Android does entertaining things on top of it after we transition to it. The on-hub router runs the Chrome OS verified boot stack inside it. So that's today. That's what's out there now. Tomorrow, really, I'd like it to be in everything. Because once it's actually in everything, once it's in those light bulbs and fridges and coffee makers and things like that, then I might actually feel safe buying one of those and actually plugging it into my home network. Because I'm very apprehensive right now. But as we move down into these devices, it gets more challenging. There's no matrix keyboard, maybe just a button or two. Maybe you've got volume up, volume down, and power. If you want to see what terrible things that causes in the code right now, go look in Depthcharge at board rush ryu keyboard.c. That's what the Pixel C does to emulate Control D and Control L via various arcane combinations of buttons. Today's Dilbert is somewhat applicable for that too. These smaller form factors don't have a display. They may only have an LED or two. And they're really, really extremely cost sensitive. So that 25 cents for a TPM and that 25 cents for Spy Flash becomes a really big part of a $20 light bulb. Where if you're shipping initially, a $400 Chromebook, now we're down to $99 Chromebooks. Well, they care about price a lot there too, but they're not quite as cost sensitive as that $20 light bulb. So what sorts of things are we doing to help with those form factors? We've already moved the screen drawing code up into Depthcharge. So instead of doing all that bitmap compositing inside of Vboot Reference, it's now happening up at the Depthcharge level. Our hope is over time that will move to something even more elegant. Maybe someone will get a convenient, relatively small SVG library in coreboot, a nicer font library, so we don't have to use bitmaps, because bitmaps really sort of limit the flexibility that we can do in the UI, especially when you're talking about things where you may want to have buttons to run some sort of simple menuing loop. We're also moving the UI loop out of Vboot Reference into Depthcharge. That's coming next as part of this Vboot 1 refactoring. Again, so we can have more flexibility in how the code works. If you look down in the guts of the display code in Vboot Reference, there are some little ugly things in there for the on-hub router. We're refactoring the kernel verification. Like I said, that Vboot 1, it's that old API based on EFI firmware and a GPT-based disk. We'd like to be able to support other storage types for where that OS kernel lives or where that next boot stage lives. Raw NAND, SPI flash, what have you. So we're refactoring that kernel API to be finer grained. We'd really like to be able to, instead of saying, hey, Vboot, go find the kernel and verify it, we'd really like to be able to say, coreboot goes and finds a couple of kernels. And it says, I found a couple of kernels. Hey, Vboot, what do you think about this one? And Vboot says, no. And coreboot says, well, what about this other one? And Vboot says, yeah, I like that one. You can run that one. And coreboot says, well, great. Could you lock any, could you update any versions for it? Because I like it too. And Vboot says, oh, okay, I can do that. So there's this lower level, finer grained API that allows for more flexibility in finding these. It also removes some of those assumptions that Vboot makes. It doesn't have to be a GPT disk where it's stored. It could just be some, these sectors of raw NAND are where this data is. And whatever additional error correction you need to do to make that raw NAND work could happen up at the storage device level, not somewhere down inside of Vboot where we would, because Vboot really wants to think in terms of give me sector 1137 right now. That's really how Vboot wants to think. We all want to take that, move that out so that we can get more flexibility. The other nice thing that we're doing as we're doing this refactoring, we're also purging that terrible coding style that we've used for Vboot 1. What we did right now is kind of this horrible mishmash of how we misunderstood the Google C++ coding style and then applied it to verified boot, except that now verified boot, everything that verified boot talks to is kernel C style. And so we have this ugly camel case and 2-space tabs and other things that make lint very sad. I'm getting rid of all that. It's all going to be beautiful and kernel C style, which also makes it a lot more accessible. If you want to come in and look at what it's doing, if you want to contribute to it, it makes it far more tractable to do it. You don't have to learn some horrible new old coding style. So verified CBFS. Right now, the read-write firmware, verified boot really wants to think of it as one big blob. And it says, okay, I've got my root key that verifies my data key, that verifies this big blob of read-write firmware. This is kind of messy. Even if you only want to use one piece of that, like the Raminit code, you still have to verify the whole thing because it's only got one signature in it. We want to fix this. There's some work that's in progress right now to break that up into pieces, to say really what we'd like to do is verify just the CBFS data structures, the metadata. CBFS at that point has a digest of each file. Each file can have its own hash digest. And then when you load that code, coreboot can say, okay, I know my data structures are fine because I asked Vboot, and Vboot said that the metadata is fine. I'm loading just the RAM stage code. Okay, that's got its own SHA-256 hash. I loaded, it's good. Oh, and now I need to display a bitmap. Okay, I'm just going to grab that one bitmap and verify its verify its hash. So we're not paying to verify all of this code, especially for the developer mode cases where there's bitmaps, there's UI loops, that code's bigger. We're not paying to verify that code every time, even though a normal user is booting the system. So it'll be elegant. It gives us more flexibility, gives us faster boot speed. And that's going hopefully straight into the CBFS side of things with verified boot sitting on top of it as the strong crypto verifying that metadata. Better support for owner versus user control. And like I said, this is a whole new thing for us in the last year or so. Our original model for Chromebooks was that we had a write protect screw. And we actually, if you look in the Chromium website, we'll actually tell you if you how to pry open the back of your case and remove that screw so you can run your own firmware. So the problem with that is anybody who has the device for 5 minutes sort of is the owner by dint of they could remove the screw. Like I said, schools don't like this. Students also have screwdrivers. And so now this is just checked in the last couple of weeks. We have this space called firmware management parameters. This is another lockable NV space. So we stuff it in the TPM. There's a flag in there that basically tells the read-write firmware, hey, if that developer flag has been set by the read-only firmware, just ignore it. Only assume that you want to go back and turn that flag off. That flag in the FWUMP, firmware management parameters, by the way, is pronounced FWUMP because that has fewer syllables. So the FWUMP is set or removed by enterprise enrollment when you enroll a device. It is not present on normal individually purchased devices. So if you go to Best Buy, if you go to Amazon, you buy a Chromebook, there should never be a FWUMP on there. Now, as a bonus for OS developers, while I was doing this, I was thinking, well, what nice things can I do? Because I'm kind of making life potentially a little bit difficult for them where they were previously able to get around the rules. What can I offer them as an olive branch? The FWUMP has an expected kernel key hash space in it, where if you're an OS developer, you can now check in the hash of the kernel data key that you want to be the one you trust. So as an OS developer previously to this, if I turned on booting, dev images from USB, any USB image would work from anyone. So anybody could walk up to my Chromebook, boot it, get a root shell. Now with the FWUMP, I can say, well, I'm going to check in the hash of my kernel key, or I'm going to check in the hash of the kernel key from this distro that I trust. And then the system's only going to obey that key. The only way to get out of that is to completely recover the device and wipe everything that's on it. So at least my stuff is secure. Docs on FWUMP are coming soon. I need to get those up on the website. Protecting content keys. So this is the next thing we're looking at. Yeah, I know. On some SoCs, the way the content keys are stored is they're burned into fuses inside the chip. And as the chip leaves its mask ROM, those content keys are left exposed, assuming that the next stage of firmware was protected when signed by the other keys that are sitting in the mask ROM. That's great if you want to have the device manufacturer lock in the keys that are usable for signing your firmware. It's not so good if you want to be a coreboot developer and actually change that firmware. So when that happens, the way it is on current SoCs, and Pixel C is unfortunately this way, the entire read-only firmware is locked down and signed by those effused keys. That read-only firmware verifies the recovery and root key matches an expected hash. If not, it clears the DRM keys before it always continues on to the Depthcharge stage, assuming that firmware at least verified. So that at least lets you on a Pixel C develop Depthcharge, but not coreboot. And we're coreboot developers, so that makes me sad. So one of the things we've talked about doing is make add a new stage before the var stage of coreboot that all it would do is look at the hash of the var stage, look at the hash of the root and recovery keys that are stored next to it, and say, if they match, I'm happy, I'll continue to var stage. If not, I'm going to clear the DRM keys, and then I'm going to go on to var stage. And it does nothing else. So this is really a tiny little stage that all it's got is the ability to hash a few little bits and clear a register. And part of why it's nice having that be such a small contained piece is we want people to independently be able to verify that that's all this new stage does. This does not have any other backdoors in it. You can compile this stage yourself and binary diff it and say, yes, I believe that that's all that this stage is doing. And again, this shouldn't stop you from installing your own DRM keys from other sources if you have them from somewhere else. And also, because this stage doesn't do anything else, it doesn't talk to the TPM, it doesn't talk to the screen, it doesn't talk to the keyboard, it shouldn't get in the way of initializing other things. There are some of the SoCs, every time you initialize something, some of those things can only be initialized once per boot. And I want to make sure that this stage doesn't get in the way and initialize things, and then you want to change your mind for whatever you want to do in coreboot, but it's too late because it's already been locked down. So that's coming soon. We're just talking about it. Would love some help on that. Other components also have upgradable firmware. There are a couple other talks talking about this. Bill's going to give a talk on some of this. Jan's going to give a talk on some of this. So I'll just touch it a little bit here. EC, the embedded controller, the USB power delivery protocol chip, they also have upgradable firmware. Inside coreboot today, there is some code that does EC software sync. And how that works is that EC, or whatever that component is, has its own read-only and read-write firmware. When it initially boots up, it's in its read-only firmware. The main processor boots up, so now we have two read-only firmwares talking to talking to each other. The main processor says, well, I can verify my stuff using the verified boot flow I talked about earlier. That read-write firmware then says, hey, CBFS has the read-write firmware I expect that component to have. Component, what firmware do you have? That's wrong. Update that. Remember, it's still talking to the read-only part of the component firmware, so it still trusts who it's talking to. Then it says, okay, now I like what you have. You can jump to your read-only half, and then everybody continues in read-only, and it's a wonderful, happy thing. So that is actually currently implemented inside of Chromebooks. We started doing that as soon as we started having our own embedded controller firmware. I'm not going to say too much more about that because I want to give Bill a chance to talk about it. But we want to be able to verify other things too. SATA drivers, remember SATA storage. There's sort of two components of devices, of components. There are two categories of components. There's things that we need for verified boot. We need the embedded controller. We need the PD chip because that's what allows us to draw more power from the adapter in the USB-C case. We might need the display or keyboard, and those might have their own drivers. So with those things that we need for verified boot, we want to verify in Depthcharge from expected read-write firmware payloads that'll live in read-write CBFS. There are some things we don't need to verify that have upgradable firmware. Wi-Fi, trackpad, the camera. We can wait for the OS to verify those things. We only really need to do software sync for the things that we need. And again, this is part of this verified boot strategy of do the minimum you have to at each step, leave as much as you can for later steps because they're easier to update. And for the EC also to make our component more secure and verifiable, we said, well, the heck of it, we'll just write our own operating system. I'd love to do that for all the components too. We're pushing component vendors to support better verification. This is a long-term battle because we are not a huge chunk of the market. What's the goal? Really, the goal here is I want coreboot and Depthcharge support for verified boot that's easy for developers to use. It should be as simple as setting a build flag, saying, oh, I need to have some keys to sign my firmware with. Fine, run a script to generate some keys. That should get you the full verified boot flow. It should be easy for you to use. We want it to be flexible enough to customize for a wide range of form factors and use cases, from laptops all the way down to light bulbs. We want there to be no excuse for device manufacturers not to have verified boot. We don't want them to say, well, verified boot looked hard, so I didn't do it. We've got this little cool security thing that we came up with, but it's closed source. You can't look at it. And if you did, you'd be horrified. We want to stop that. We want this stuff to be open source for both the OS and the firmware. And transparency really matters there. One of the big things about open source, not just that we can tinker with things to our heart's content, but we can also verify that even those things that we don't tinker with are doing what they claim they do. And we also want to make sure in all of this verified boot that it doesn't come, that the security doesn't come at the expense of locking these things down. It doesn't come at the expense of using all these e-fused keys to where we can't do open source development on these real cool devices that we get. So in terms of how you can help, look at what we've done. The more eyeballs on verified boot code, the better. Question our assumptions. Like I said, I've said, here's what we were originally thinking. Here's kind of what we're thinking now as the use cases changed. What are we missing? You may see use cases we don't. You may see things that we thought were locked down and simple that are actually not quite so simple. If you want to help contribute, I would love to have help on a lot of these things. Graphics libraries, so that we can do better UI screens on things that don't have matrixed keyboards, verified CBFS, a DRM clearing keys stage, things like that. Think about security, particularly if you're working on those early boot stages, where if you're in those really early boot stages, they're harder to patch. And definitely keep being awesome. All the stuff that I've done with verified boot, it's largely a reference library. Without something to plug into, without coreboot, it's just a reference library. And if we can get coreboot everywhere, that means it's a lot easier for me to stuff verified boot everywhere too. So thank you. Any questions? Ooh, I'm good on time.
How do you know that your proverbial light bulb indeed runs whatever verification scheme you have?
So some of this, since you didn't have the mic at the time, so the question is, if you get a light bulb, how can you be sure that it's actually running the software that you think it is? Some of that is we have to make sure with these devices that they have a way to actually read out what's on them. A recovery mode that we can believe in, something where we can actually read out. It may not let us, when it's in its verified mode, write what's on it, but we should have a way of verifying those components. Jan's talk goes into a bit more detail on some of the things that we're doing there for how do we verify those bits.
Okay, another question is, on x86-based Chromebooks, do you plan to make use of BootGuard? Because reflashing SPI, even though you can have a grounded write protection pin, reflashing SPI is just a matter of 5 minutes, right? So yeah, students with screwdriver can do that.
Right. Yeah. If you have a screwdriver and you go to eBay and you pay $20 for the DataPro, the USB to SPI chip that you can buy off of eBay, yes, you could come in, pry the device open, rewrite the SPI flash, and own the rest of the system that way. The tricky bit with BootGuard is that that's a sort of akin to the eFused keys, and the mask ROM. It's good for content providers, good for people who want to control the devices, a little bit less good for us as open source developers. There are some other clever things that we're doing that I can't quite talk about yet that will also help address that use case in the board design.
Can't you just
layer.
Use BootGuard to lock down only your first stage loader, the one that you keep in your read-only partition on SPI?
Yeah, potentially we can do that. Just like I talked about with that initial stage of clearing the DRM keys. The first stage there has to have enough smarts to be able to hopefully turn on and off a developer switch so that it knows whether to run the official content or run our own firmware on top of it. In other words, how do I know that the light bulb I got, I can trust that it runs that initial stage because it's boot guarded. I need to have some way of being able to assure, is that running the official code? Is that running this distro that I downloaded? Or did somebody else return, buy the light bulb, install their own stuff, and then return it to Fry's, because nobody ever returns anything to Fry's Electronics. How do I make sure that this thing has still got what I want it? So it is still a hard problem, yes.
How does Intel ME and friends fit in that picture?
Horribly.
Sorry for that.
Yeah, I actually, amusingly early on in the development process for the Chromebook Pixel, I actually did have code where the embedded controller had access to the SPI bus. And I thought, well, okay, the ME wants to rewrite its firmware, but it insists that part of the flash be rewritable. But I can have a read-only copy of it over here. And when the EC comes up in its read-only mode, it can compare and put back the bits that I wanted it to have. So things like that potentially are sort of end runs around the evil management engine, or potential evil management engine. But more or less in there, you more or less may have to stick in a secondary component to sort of watch the watcher at that point to make sure what's going on.
But even if you do that, according to your first words, you cannot trust it, because you never had a look at the firmware, what's really do it. I have seen one APM running, and it's incredible.
Yeah, there's anytime you're running code you can't see and verify, you sort of have to take on faith that it's only doing what it claims it does, and you're acting in your best interests. Gosh, it's nice that we have a whole bunch of ARM chips that are coming up. Maybe we could run a completely open source hardware architecture.
Like that's ever going to work.
So hopefully there are ways around that, and as those things become more capable, that'll also put some pressure on making the things we have now more open. I mean, this is by all means not a short battle. We've been fighting it for 7 years. I anticipate fighting it another 10. Anybody?
You're such an optimist.
Well, after 10, I'm actually planning on retiring, going to a tropical island and scuba diving all day. The battle may not be won, but I will have passed it off. But I will have stopped fighting it.
On that island too. That's a very sensible approach.
I hear Stefan's actually going to buy us an island for coreboot. So.
It's going to be coreboot island. With the quad supplies, the write protected pin is multiplex.
Yes.
So you have to have some transition from moving to SPI to some other storage.
Right. So the question is, on Quad SPI, they cleverly multiplexed that write protect pin. We just actually don't use Quad SPI boot mode in any of our Chromebooks for any reason.
Okay. So you can control new
like Chromebook or whatever designs and
That's
tell them
one
not
of
to
the
use that
nice
spy?
things about Chromebooks
Okay.
is we have a little bit more control over how the hardware gets put together.
I guess the other thing is like when you say you read-only lock the partitions of the SPI, you're kind of at the mercy of the SPI controller. So if there are any other components that are running side by side at runtime and you're not verifying what runs on those, they could potentially at an arbitrary time use the SPI controller to remove your guarantee of read-only.
So the read-only that we're getting in the SPI, so the SPI chip itself has its write protect pin. It's got the control register in it, and the control register in that SPI flash is like 16 bits of configuration, and that specifies, do I want to lock the top half, the bottom half, or whatever. One of the bits in that register is, if I set this bit, don't let any other changes happen to the control register until that write protect signal is physically electrically deasserted. And so that's why we believe SPI write protect, because even if you're we're not just using the SPI controller on the chipset to say, hey, SPI controller, don't allow writes to these regions. We're using that discrete logic on that SPI flash chip itself.
Nice. I would say, so the last thing, you said glitching is a little out of scope. I would argue to bring it in scope a little bit, because although preventing the initial like glitch bug discovery is kind of hard to fight against, but the productization of a glitching attack might be something that like Vboot 2 could try to battle.
Yeah.
Like bringing everything into the SRAM before you do your verification.
Yeah, we actually do. All of the code that we read right now, we read into RAM and then we verify each step. And that actually helps us. The bad USB attack that came out last year, where you have a USB stick and it's a storage controller, and the first time you read this sector, it gives you one answer, and the second time you read it, it gives you second bits. The Chrome OS verified boot scheme always reads stuff into RAM, then verifies it. It doesn't trust what was on the disk anymore. So we actually lucked out. We want to claim that we thought of that ahead of time, because we actually kind of did. But yeah, we have to worry about that. A lot of the other hardening against those harder attacks are complementary to verified boot. Nothing about what we're doing here prevents somebody from locking those things down more. We've just been focused more on this part of it. Also because a lot of the hardening against those harder attacks requires sometimes more expensive components, more expensive board design, pop the EEPROM in epoxy so you can't just clamp it. There are things, it all plays together. You can do both.